like 2, 8 in base 16, which we don't say 28. We try not to say that, right? This is saying 2 and an 8 in base 16, and each of those have their own different values, as we will explore a little bit more in a second. So there's two advantages of using hexadecimal as opposed to binary. One, which is kind of a really valuable one, is that hexadecimal takes fewer digits to represent a number than when compared to binary, right? When we think back to the problems that we were doing in the last exercise, if we wanted to represent a number like 172 in binary, we needed 8 digits to be able to do that. We're going to see that in hexadecimal is going to take far fewer. And the other advantage of hexadecimal is it's very easy to convert in between binary and hexadecimal in a way that it was not easy at all to convert in between binary and decimal, as we saw in the previous section. We're going to see there's a very standard way to go about converting between binary and hexadecimal. So we learned the powers of 2 back for dealing with binary, and for hexadecimal, we are also going to have to learn how to work with powers of, well, 16. So, and when I'm writing these numbers, of course, I'm using here decimal notation. So just a quick aside, when we see all these numbers, I'm going to omit the base 10 in the bottom right-hand corner, and we'll just recognize that each of these represents some sort of decimal number. So in decimal, when we have 16 to the power 0, we of course know that's just 1. And 16 to the power 1 is just 16. Now here's where we might need to get out our calculator to start doing these. So 16 squared works out to be 256. If we multiply that by 16, we get 4,096. And if we multiply that by 16, we will get a whopping 65,536. Now, let's think about how to write that as an equivalent power of 2. Well, the first one is not particularly exciting, right? Because if we are thinking about the number 1 in decimal notation, it's just 2 to the 0. And what we saw before, and what we noted just above here, is that 16 is equal to 2 to the 4. To fill out the rest of the rightmost column, it might be helpful for us to remember one of our exponent rules that we mentioned back quite a few sections ago. So if I have a to the m and I take that to the nth power, I get a to the m times n. In other words, I'm going to multiply those two exponents. So when we see here 16 squared, we think about that as, well, 16 we know is 2 to the 4th. So it's 2 to the 4th that we're squaring. Well, if we go ahead and multiply those two exponents, the 4 and 2, 16 squared is the same thing as 2 to the power of 8, which, as we did see in a previous section, was 256. And similarly here, 16 cubed, well, 16 we said is 2 to the 4th. So if we cube 2 to the 4th, multiplying the 4 and the 3, that's the same thing as 2 to the 12th. And over here, we've got 2 to the 4th, is that 16? That's being taken to the 4th power. When we multiply those two powers, we get 2 to the 16th. All right, so let's do an exercise kind of like what we did back in the first section we were working on, which is to write a hexadecimal numeral using a base expansion and write the equivalent numeral in decimal. So when I see 239 in base 16, remember that those indices, right, the index, which would be 2, 1, and then 0, tells me the power of the base that I'm working with. So I'm going to be working with 16 squared, 16 to the 1st, and 16 to the 0 here. That 239 in base 16, the first digit, is being multiplied by 16 being taken to the 2nd power. The next digit is 16, the number of just 16s that I have, and then the last digit is just itself, right? And note all these numerals here we're representing as decimal values here. So 2 times 16 squared, that's going to be 2 times 256, because that's what we just said 16 squared was. 3 times 16 is 48. Well, if we double 256, we saw that in the previous section, that's 512. We're going to add 48 to that and then add 9. That's 560, so if we add 9 to that, we will get 569. So we see that number, that numeral in hexadecimal 239, then we know that that is 569 in base 10. So, by the way, one of the things that I learned in the process of doing this is that a lot of times in computing, we don't use this little subscript to indicate a hexadecimal numeral. It's kind of tedious to denote subscripts. So instead, the prefix OX will be used to note that a number is in hexadecimal. So we could write this thing as OX 239. I encourage you to Google that to verify that that does in fact work. All right. So we're going to note, however, one of the things that hexadecimal poses that's a challenge when compared to binary is that with decimal, we had 10 digits to work with, right? 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And binary, no problem, right? We're only using 2 digits, so we're only going to use the first 2. But hexadecimal, we're going to try to write 16 different digits. So the problem is that we only have 10 symbols to represent those first 9 digits. But we're going to have to represent the numbers 0 through, remember we can represent up to 1 less than the radix here, so it's going to have to represent 0 all the way up to 15. And what that means is that the numbers in decimal, 10, 11, 12, 13, 14, and 15, are going to need to be associated with 1 digit in hexadecimal. If you've seen this before, this may be very familiar to you. So we're going to denote this with capital letters. So capital A is going to be 10, capital B will be 11, capital C is 12, capital D is 13, capital E is 14, and capital F is 15. So remember always, once we get to that last digit we can express as 1 less than the value of the radix. So we see that written out here, that the decimal digits A through F correspond to the decimal numerals 10 through 15. So let's use that table here and that new convention to do a couple of similar problems, convert these hexadecimal numerals, into a decimal numeral. So when I see 8F in base 16, that 8 tells me the number of powers of 16 that I have, and then we're going to add to that F. Well, if we want to express that as a decimal numeral, F, the largest digit I can express in hexadecimal is 15. Note we got 6 letters that are also denoting their own digit here. So 8 times 16, if we add that to 54, you can double check that 8 times 16 is what? 8 times 8 is 64, and then if you double that, you get 128. So add 15 to 128, you'll get 143. Again, when I say 143, I mean in base 10. Now what about if we have 2E0B in base 16? So if we want to write this hexadecimal numeral, well, note that I've got 4 different digits here. So my index is going to be 0, 1, 2, and 3. So I'm going to have 2 times 16 to the 3rd power. And then I got E here. Well, again, from the table, E is equivalent to 14. So we've got E, oops, I don't want to write E. E isn't the thing that we are thinking about in decimal. I want to write it as 14 times 16 being taken to its index, right? It's the second index. So we got to go 0, 1, 2, 3. And then we will add to that 0 times 16. Of course, 0 is not going to contribute anything. And then we're going to add B to that. Well, B is worth 11 by itself. On the previous page, we noted that 16 cubed was 4,096. 16 squared is 256. And then we'll add 11 to that. If you double 4,096, you get 8,192. I'll let you check this in a calculator. If you do 14 times 256, you end up with 3,584, and then we'll add to that 11. So when we carry that out, if you add all those numbers up together, you'll get 11,787. That's going to be base 10. I'm going to get my calculator out to make sure I have it. We're going to need it in a little bit. There we go. One more example here. Let's convert the hexadecimal number C00A into a decimal numeral. Well, just like we did in the previous one, we know we got 4 digits, so that first one has an index of 3, one less than the number of digits that we have. So C is equal to 12, so we're going to take 12 times 16 to the power of 3. We've got nothing times 16 to the power of 2, and nothing times 16 to the power of 1. And then we're going to add A to that. But again, remember, A is not a decimal numeral. We have to think about A as being representing the number 10, when there are 10 things, like 10 fingers on my hands. All right, so we've got, again, 12 times 4,096 plus 10. Just do that one together. 12 times 4,096 plus 10. We get 49,162. We can note something here, that hexadecimal, given the fact that we can represent more digits in hexadecimal, it means that we can often represent larger numbers with a smaller number of digits, right? Decimal took 5 digits to express it, when hexadecimal only took 4. When we compare hexadecimal to binary, we are going to see that it is far, far, far more efficient. We'll talk about how to do that in a little bit. So there's kind of 2 main things that we want to do in the duration of this section, right? This first thing is kind of a little bit of review. It's just that the only thing that's new is the fact that hexadecimal has 6 new digits that correspond to the numbers 10 through 15. So we also might want to go backwards, right? Here's a little tricky bit. Now, the convenient part is that we can follow a very similar argument to the one that we encountered in the previous section on binary. There's going to be one additional step to doing that. So let's talk about this algorithm by way of an example. So for instance, suppose we wanted to convert the decimal numeral 217 base 10 into a hexadecimal numeral. The conceptual idea that we're trying to get at is that this is equal to some number of 16s plus some number of things left over. And the way that we're going to do this is we're going to start by, instead of dividing by 2, like we did before, we're going to divide by 16. Now this part's a little bit weird because here's where we have to get to learn our calculator a little bit better, right? And depending on what your calculator exactly is set up to do, when you divide 217 by 16, chances are you're going to get a decimal like this, so 13.5625, right? Remember, we talked about, let me shift the focus a little bit here, so you can maybe see that a little better. There we go. All right. So in other words, we get a result of 13 with some remainder. Now, depending on your calculator, you actually have a button that'll allow you to tell how to do that, but if you don't, we have to get a little bit creative. So let's think about what this means, right? When we divide 217 by 16 and get a result of 13, remember division is the opposite of multiplication. So this is saying, if I took 16 times 13, that's the biggest number that I can get and still be less than 217, right? So if I take 16 times 13, I will get 208. So 217, when I divide it by 16, I get 13, but that only takes me to 208, so I have a remainder of 9. Here's another way to do that with your calculator. So you can think about it like reverse process. You know, if I look at this divided by that, I get some result. If I take just the whole number part of that and multiply it back with the thing I was dividing by, I just have to figure out how much less is it than what it was before. The other way that you can do that, because your calculator is fancy, probably, in some respect at least, is if I were to take away the 13, right? I know this goes in evenly 13 times, so I could subtract that 13 bit away. I've got this decimal equivalent that is equivalent to some number of 16ths. If we think about this thing here for a second, the 0.5625, it's equal to some number of 16ths. Well, the number of 16ths we could find by doing a little bit of algebra. Multiply 16 by 0.5625, right, and get 9. Or what your calculator is doing is basically the same thing. I can use a fraction to decimal part with this decimal bit that's left over, and my calculator tells me it's 9/16. So that number there, 9, tells me the remainder here. Okay, so that was the part that was sort of like we did before, but we had to mention a little bit more because the remainder here is a little trickier to find when we're dividing by 16. The one extra bit that we're going to have to do here in this step is think about, remember the remainder in the last algorithm was the thing that told me the digits of the hexadecimal number. So we are going to have to think about what that digit is in hexadecimal. Well, 9 in hexadecimal is just 9. But now, this last one, right, we take the result, we try to divide it by 16. Of course, that's not going to work. We're not going to get anything out of that. So then the remainder will just be all of that 13. We can't divide 13 into any number of 16, so we're left with all of those as the remainder. So now we have to remember what the hexadecimal digit that represents the decimal numeral 13 is. So remember, once we get to 9, we start counting that 10 is A, so then 11 is B, 12 is C, and 13 would be D. The very last thing that we do is just exactly the same as we did in binary. The digits of the hexadecimal numeral are going to be the remainder, read from bottom to top. So the way that we'll write this number is as D9 in base 16. Let's do another example. Convert the decimal numeral 574 to a hexadecimal numeral. All right, so if I do 574, first thing I want to do is divide that by 16. So when I do that, I'm going to get a result of 35 with that 0.875. So again, think about dividing 16 by 15. I'm not making you do long division here, but if we did 16 times 35, that would get me the largest number that is less than, the largest multiple of 16 that is less than 574, right? Note that we couldn't have another 16 in there because that would take me to 576, which is too big. So I get a result of 35 times 16 is 560 is the largest number that is divisible by 16. It can be split up into 16 parts. How many parts do I have left over? Well, it would be 14, because that's the value of 574 minus 560. By the way, this process of talking about the remainder, we're going to have to come back to this because it turns out the remainder is actually a really key idea in a lot of computing that we've already seen. So hexadecimal digit of that remainder, well, remember 13 was equivalent to D, so 14 is equivalent to E here. All right, next up, I'm going to take the result here, 35, and divide that by 16. If I divide 35 by 16, I can do this one, not too difficult, right? That will go in twice. 2 times 16 is 32, so I'll have a remainder of 3 left over. And, well, the hexadecimal digit of 3 is just 3. Lastly, I take the result, try to divide that by 16. It's not going to work. I can't divide 2 by 16 and get anything left over. So I get a result of 0 and just have the remainder being 2. and the hexadecimal digit of 2. Again, any digit 0 through 9 can just be represented as the exact same thing. So this digit, reading from bottom to top, would be 23e base 16. Last example here, let's convert 7,183 to a decimal numeral. All right, numbers getting a little bigger here. 7,183, divide this thing by 16, I get a rather large number of 448. So just to show that other process, the other way we could do this thing, if I subtract that 448 out, and I just focus on the decimal portion that's left over, and I convert that part into a number of sixteenths, I get that that's equal to 15 sixteenths. So when we divide 7,183 by 16, we get 448 evenly with a remainder of 15. Now the hexadecimal digit of that 15 is our greatest digit in hexadecimal, which is F. Continue this process. 448 divided by 16, we get, oh, that one actually worked out nicely, 28 with a remainder of 0. Well, 0 in hexadecimal is also 0. Take 28 divided by 16, we get 1.75, so we get 1. Well, let's think about this. So just to have like a slight cautionary note, right? If you try to do that one method of subtracting that bit and then converting between fraction and decimal, you get 3/4. But we really need to think about 3/4 as being a certain number of sixteenths, right? Doing a little proportional reasoning here, if we multiply the denominator by 4, I gotta do the same thing with the numerator, so that's 12 sixteenths. So just be careful if you are doing that, subtract away the result and then convert the remainder back into a fraction. You do need to think about that in terms of how many sixteenths you have. That also is probably slightly overkill on this particular example, because if you divide 28 by 16, 16 will go in evenly once with a remainder of 12 left over. Again, starting counting with 10 being A, 11 is B, and 12 is C. Last, we take our result of 1, try to divide that by 16, not going to work. We're just going to have all of that left over, and the hexadecimal digit will then be 1. So the number 7,183 in hexadecimal will be represented as 1C0F in base 16. All right, so as we can see, this is kind of probably the trickiest aspect of this. It's like binary. It takes a little less time to convert, but we have to think a little bit more carefully because we have to really, really remember how exactly to carry out this, how to find the remainder when doing division. But the nice bit that we will end this section with, again, we will talk a little bit more about hexadecimal and binary in the next couple of sections, but the very last thing we can do here is convert in between hexadecimal and binary. And there's a nice convenient table that we can use for this. Now, before I look at the table, one thing we can note from the last section, computers fundamentally, our standard normal kind of computers, are coded using binary code, right? Things are either off or on, 0 or 1. But binary numerals are really tedious to write out, right? With 4 binary numerals, the highest that we can count to is 15, right? Anything from 0 to 15. So programmers will typically avoid doing everything in binary, just because it takes a long time. Instead, they will use hexadecimal as a sort of abbreviation. So here we got the hexadecimal that is equivalent to the various binaries. So I've got all the numbers in binary from 0 up through 15 in decimal, and then the also equivalent hexadecimal. So if we just look at these two columns give me a way to go from binary into hexadecimal. And here's the neat thing that we can note is that this is all of the binary things that we could express with 4 bits. Those are all the binary numerals that are 4 bits. And we could note that all those 4-bit binary numerals can be converted into 1 digit in hexadecimal. So hexadecimal is basically like 4 times as compact in terms of expressing information here than binary is. So remember, 1 byte from the last section we talked about was 8 bits. So if 4 bits can be expressed with 1 hexadecimal digit, then that means 8 bits can be expressed using 2 digits in hexadecimal. So let's do a couple of examples like that. This is going to be a lot easier than the math that we just did because there's no weird remainder stuff to work through. All we have to do is locate our spot in the table here and convert digit to digit, or rather string of 4 digits. So here I've got 2 strings of 4 digits, 1011, 0100, sorry, 0110. The first 4 digits, we recognize that right here, that's equal to 11 in decimal. In fact, we can do a quick double check, right? 1 plus 2 plus 8 is 11. 11 in hexadecimal is B. And here, this one again, we can think about this. This is equal to 2 plus 4, which is 6. So 6 in hexadecimal is just 6, right? So you can consult the table, but really what it comes down to is just these both represent some underlying number. And if you can think about what that underlying number gets represented as in hexadecimal, you kind of don't even need the table. Just for good measure, we'll go ahead and write the little 16 down in the bottom there. We can also see something like this, 0011, 1000. Well, let's see, that would be, here's the first string of 4, here's the second string of 4. 0011, well, that's 1 plus 2, which is 3. And then this one right here, 1000, well, that's 8 plus nothing. So that would just look like 3, 8. Again, that's where it's very, very important to make sure that in some way we are signifying that this thing is a hexadecimal value here. And we could go in the reverse direction with about the same amount of difficulty here. If we want to convert this thing into binary, well, this one's a little trickier because now it's helpful to be able to think about how to convert from hexadecimal into binary. That first hexadecimal digit of E is equivalent to 15, and the way that you get 15 is with 1814, 15 is right down here. That E is 14, I said that incorrectly, my apologies. E is 14 in decimal, and the way that we get 14 using our coins of 8 cents, 4 cents, 2 cents, and 1 cent is 1 8-cent coin, 1 2-cent coin, 1 4-cent coin. I said that in the wrong order, but that E, which represents 14, is represented with a binary digit, 1110. And A, which is 10, is going to be an 8, no 4s, 1, 2, and then no 1s. Write that little base 2 down there. Remember, the space doesn't really signify anything. It's just to make it a little bit easier to read. One last example here. A5DF in base 16. Well, we just did A a moment ago. That's 1010. 5 is going to be no 8s, 1, 4, no 2s, and 1, 1. Or again, you just look up to here. D is 13. And 13, we're going to have 1, 8, 1, 4, no 2s, and 1, 1. Or again, just look at the table here. And then F is 15, and that's going to be maxing it out. Right, so just like this is the largest binary number we can express with 4 digits, F is the largest digit we can express in hexadecimal. So there we go. So we see that a string of 4 hexadecimal numerals, since each one of them is 4 of them would be 16 digits in binary. So that's all we have for this section. take some time to make sure you get practice with doing these various conversions, because in the next couple of sections, we're going to look at a couple of algorithms in binary and hexadecimal, namely addition and subtraction, and then we're also going to look at a few various applications to binary and decimal. So, binary and hexadecimal. So see you soon.